Okay, so the actual affine transformations are transformations that actually preserve points, meaning that if I have a triangle and I do some kind of a transformation to it, I end up still with a triangle. Now, it doesn't mean that the angles are all the same or that the distances are all proportional. It just means a triangle becomes a triangle. A square may be a rectangle, may be a square, but it's still a four-sided figure. And it could be many things. It could be rotation, mirroring that happens to, if I scale it, if I do a translation, if I do a shear, which is not part of our syllabus directly, but perhaps they may lead you through something like that. But you would just have to make that connection for yourself, or a non-uniform scaling, so a K001 scenario or a 100K type scenario. Okay, and so we've looked at all these scenarios. These ones here are multiplication of a sort, and the translation is when I add a vector onto it. Okay, and so this one here is the translation. They can all be written, affine transformations all be written as a matrix equation like this, or a matrix equation like that. So let's try an example of one. So points in the plane are rotated anticlockwise about the origin through 60 degrees, and then translated +2 in the x direction, +3 in the y direction, and this is the equation for it. Find the exact value of the constants in matrix A and B. Well, from here, this is matrix A, and this is matrix B, which I can see from this equation. So matrix B is quite easy. It's +2 in the x and +3 in the y. So I know that B will be 2 and 3. The rotation in the anti-clockwise direction through 60, well, I know that this is my formula for rotation of 60 degrees. And I know that from my formula booklet. And if I look down here, it's cosine theta minus sine cosine theta if it has a rotation of theta degrees. And so if I do the computation there, I can say I know that A, this is A will be 1/2 √3/2 minus √3/2 and 1/2. I have these values memorized. You can use your calculator, but if you memorize them, it'll be really quick for a lot of things in your future world. If I'm going to find the exact image of the point 2, 4, what I'm going to do is I'm going to take this matrix here, which is my ABCD, and I'm going to take it, I'm going to multiply it times 2, 4, and then I'm going to come along and add matrix B. Matrix B, which is over here. And we'll erase this part of it. And I'm going to add, multiply, and add. And when I do that, I end up with, if I do the multiplication, 1/2 times 2 minus 3/4 over 2 times 4, I end up with a value that is 1 minus 2 √3, and the bottom will be √3 plus 2. This point plus a 2. And when I put them together, I get 2 plus, or 1, sorry, plus 2 will give me 3 minus 2 √3. Remember, I cannot add these numbers together. And I also can do the last bit, which is going to be square √3 plus 5. And so here is the new point. This is the image point of 2, 4. Okay, B part then, or C part rather, I'm going to switch to purple. C part now says find the exact point that has this image. So now I have to work backwards. I'm looking for x, y. This is my image point. And so what I'm saying is that 4 plus 3 √3 and 2 √3 is equal to this this is a true statement for C part. And so now I have to go about, except I have to, this is going to be my x and my y. And I have to solve for x and y. In order to solve for x and y, I'm going to subtract this vector over. I could think about it as x prime is equal to ax plus b. And so I can subtract my b is equal to ax. And then what I'm going to do is I'm going to multiply by the inverse of a here in front, and then here in front, a inverse. And this should get me my answer. That's the theory I'm going to do. So I'm going to subtract over the 2 and 3. So 4 plus 3 root 3, 2 root 3, minus 2 and 3 is going to equal to 1/2 root 3 over 2 minus root 3 over 2, 1/2 xy. This is simply, I'm subtracting these, so I get 2 plus 3 root 3, and I get 2 root 3 minus 3. This is equal to 1/2 root 3 over 2 Now to find for xy, I have to find the inverse of this matrix. So if I'm going to find, and I'm going to have to multiply the inverse, is going to be here and here in front. So to find the inverse, I'm going to go find the determinant first. 1/2 times 1/2 is 1/4. So it's 1 over the determinant minus root 3 over 2 times a negative root 3 over 2, which is a negative 3 over 4. I switch these two around, so 1/2 and 1/2, and I change the sign, so this is root 3 over 2 and a negative root 3 over 2. And this will equal to xy. Well, 1/4 plus 1/4 is 1, so I can really ignore this part. And I forgot to write this matrix. I went too many things I'm thinking about. So I have to multiply that times 2 plus 3 root 3, 2 times root 3 minus 3. And when I multiply that, I will then get my xy. Multiplying this, well, it's going to be 1/2 times 2 plus 3 root 3 plus root 3 over 2 times 2 root 3 minus 3. This will be my x value. And I'll simplify this first. So that's going to be 1 plus 3 root 3 over 2 plus, that's going to be, the 2's cancel. I get 3 minus a 3 root 3 over 2 is equal to x. Well, happily, those cancel. And so I can say that x is equal to 4. When I'm going to find the y values, I'm going to go minus root 3 over 2 times 2 plus, and then I go plus 1/2 times 2 root 3 minus 3 is equal to my y value. So doing this multiplication, I get negative root 3. This will be negative root 3 times root 3 is 3 times 3 is 9. So 9 over 2 plus the 2's cancel, give me root 3, and minus 3 over 2 is what my y value is. Conveniently, the root 3's cancel away. This is negative 12 over 2, which is a negative 6. And so xy, the original point was 4 comma negative 6. So we use our matrices. We use our rotation matrix, our translation, and then we work our matrix algebra backwards to solve for our image point.